here because I know Josh really well, and let me tell you, Josh is probably he is the most interdisciplinary person I know, and that coming from me is saying something.
Good, thank you.
Is he a political scientist? Is he an infectious disease expert in public health? Is he an economist? Is he an archaeologist? All of these things you might, in certain contexts, answer yes to. When you want to start a revolution, he's your guy. When you want to know what happened to the Anasazi, he's your guy. When you want to know how to evacuate Seattle during the zombie apocalypse, he's your guy. This kind of spread of things that he has done is truly amazing. And sort of formally, I could talk about some of his many affiliations. He's currently at the School of Public Health at NYU. Before that, School of Medicine at Johns Hopkins. Before that, running the Center on Social and Economic Dynamics, one of the most pioneering places for agent-based modeling at Brookings with Bob Axtell, where they also developed Sugarscape, which I should always give my ad. Crafting good agent models is a very difficult task, and we all know that. Sugarscape is one of the most well-crafted models for getting a lot of information out of just enough detail in it. If you have not looked at Sugarscape, definitely do that. And then he has also written 3 books, which we should call the foundational trilogy for agent-based modeling, reference to Isaac Asimov.
Thank you. Honored.
There. And also, Josh always told me, and I think he's going to, I would also, I'll end with calling one of the sort of great theorists of agent-based modeling. Obviously he's done lots of applied stuff, but he has also done a lot of theoretical thinking about what this whole field is all about. Josh has a quote, which I will badly quote because I'm going to tell you that it's right, but I don't remember the exact words of, if you can't generate it, it's not real. He may even say that today with correct words, but a whole lot of us know what he's talking about when he said that, and it's always echoes in my head too. So Josh, I can say many, many things. We also have affiliations with Santa Fe and Indiana Complexity Hub, and those two. But anyway, it's all yours.
Well, thank you. I'm honored. Thank you. Well, thank you all. It's a great pleasure to be here. I just wanted to thank Uri for his brilliant ongoing career in NetLogo, which has meant a huge amount to me and to our community. And just let's keep it going. That's my attitude. So today I want to talk about one of these theoretical things that Blake was telling you about. If I can get this thing to cooperate. Let's see what we got here. Yeah, I want to talk about an idea that I've been working on for quite a while that I call the Generative Explanatory Atlas. And there are quite a few sections of the talk. I don't need to enumerate them, but I'll go through quite a few related topics. But first, what's the motivating question? This is the quote, Blake, but whatever. And the motto, and I coined this phrase, if you didn't grow it, you didn't explain it. And what that means, we're thinking of rule-based systems, such as ABMs, where we explain macroscopic phenomena, distributions, epidemics, economic trajectories, spatial patterns. We explain them by generating them from the bottom up in populations of interacting software individuals. So compactly, a motto for this enterprise is, if you didn't grow it, you didn't explain it. So the motto says, if you didn't grow it, you're not an explanatory candidate. So growing is a necessary condition for generative explanatory candidacy. And I wonder, can we do better than that? Can we require that a rule not just grow the phenomenon, but grow it robustly, stably, in some sense, to be discussed? In particular, we have all these models where you devise these rules and they generate some phenomenon. And it's a fair question to ask, What if you change the rule a little? Do you still grow the phenomenon? And I'm not talking about change the initial conditions, like the starting number of agents, or change the numerical parameters, like the probability of transmitting the disease per sneeze. We know how to study those, and NetLogo behavior space is marvelous at that. But I'm not talking about changes in parameters or initial conditions. I'm talking about a small change in rules. And I think agent-based modeling lacks a theory of stability in rule space. And to bore into this today, I'm going to make several important simplifications. One is that we're just going to imagine an agent as a single rule. The agent we're going to identify with their rule for now. And it's the same rule for all agents, as in cellular automata that you just learned about. Even with a fixed rule, what actually unfolds as we iterate the model forward, sorry, I interrupted the video with that. Even with a fixed rule, what actually unfolds as we iterate the model forward in time certainly depends on the interaction space and the size and the number of agents, the parameters, whatever updating protocol you're using, the time horizon of the model. I'm going to call all of those gamma, and then in time the model acts on rule space cross gamma. So iterations take you from rules and parameters to outputs of the model, segregation, time series, distributions of wealth, what have you. Today we're going to ignore all of this stuff in gamma, this whole rack of things, the number of agents, the parameters, and focus purely on the effect of rule change only. We're going to treat, rule change ceteris paribus, as economists would say. And you could think of gamma as a unit vector, however you'd like to think of it, but today I'm just going to try to bore into this issue of rules. Okay, good. Now, when we run the model, when we hit go in a NetLogo model, we track state change over time. How does the state of the model change? The number infected, the number dead, what happens? And we always do is typically in discrete time, ticks, so forth. Iteration is a function of time and is obviously discrete, not continuous. When we set the rule and iterate the model in time, we get some output. If we change the rule and run the model, we get some other output. The mapping we want to study today, the generative map, is not a function of time, but a correspondence between rule space itself and outcome space. So the generative map is between rules and outcomes. To construct a G, of course, you iterate the model forward in time given the rule. But G itself is not a function of time. It's a correspondence between two sets, rule space and outcome space. And we'll see that map can be continuous in a rigorous and very fruitful topological sense. So subject to all of this, the question was, what if I change the rule a little? What should I mean by a small change in rules? And this has been on my mind for about 30 years. I raised this question in 1999 and raised it again several times since, and most recently in our inverse generative social science work in 23. And it seems like an innocent, clear question, right? Small change in rules. So, let's, for example, I have the rule eat a potato, and I change to flee green things, or I change to obey your mom. Are those small rule changes? What do we mean by a small rule change? And of course, we're typically trying to explain some macro pattern. That's the it you're trying to grow. If you didn't grow it is a segregation pattern or some macroscopic pattern. So a natural temptation would be to define a small change in rules as follows. A rule change is small if and only if it generates a small change in output. That sounds like a natural move, and it's absolutely failed. If that's your definition, then it's not logically possible to coherently assert that a small change in the rule produced a large change in output, something we care about a lot. This is defined out in that definition because I've said a small change in rule if and only if it's a small change in output. So I can't coherently say I made a small change in rule and a large change in output. And for the same logical reason, I can't say that a large, non-small rule produced a negligible change in output. So I have these cases where a small change in rule, large output, large change in rule, small output, those are precluded by this natural definition. Okay? So what do? To talk about the stability of output to a small change in rules, we have to resist the temptation to interdefine the metric on inputs with the metric on outputs. Each set, rules and outputs, requires a separate metric. And for outputs, this is, pretty off the shelf. For the macro things we like to grow, distributions, segregation patterns, we have metrics, Kolmogorov-Smirnov score on distributions, Moran's I for clustering, mean square error over a time series. We have a lot of ways to do that. And for reasons that will be evident, let's just agree that for purposes of this talk, an output is an open set, like a range of Moran's I values, or a range of mean square errors, or you grew the observed thing if the Kolmogorov proximity is between the empirical target and the model is less than some threshold. I succeeded in growing it if it's within some distance of the target. Okay? And we're going to assume that that makes this, we're going to call these open sets. We're going to make them open sets, assume they're open sets. Now, rule metrics are less easy. There are a lot of candidates. What do you mean by, the distance between rules? One move is we're going to represent rules as trees. So here's a tree encoding of the decision to move. So it could be, are you unhappy? No, then stay where you are. If you're unhappy, yes, then you say, well, is there any place to go? And if there isn't, you stay. And if there is, you go there. But this rule, this movement rule, is a tree. And I just want to stop for 2 seconds and just, for those who aren't familiar with it, between open sets, what is an open set? The right, if this is all dense, imagine these dense little elements, dots, members of the set. Then every neighborhood is entirely in the set for an open set. A closed set, that's not true. The left is closed for boundary points, like enclosed in this circle. Points on the boundary, it's not true that there's a little radius within which everything stays in the set. To the right, it goes out of the set. To the left, it goes in the set. An open set, everything is in the set. I can always find a neighborhood of rules, elements that stays in the set. Okay, so this is all preliminaries. Later, I'm going to go back and forth between a very high-level general discussion and a very particular instance for agent-based models. So I'll give you a specific metric, a little bit, called the cylinder metric on trees. And since we're identifying rules with trees, it's also a metric on rules. And we use that to prove that the inverse of the generative map is open. And by a very beautiful theorem in topology, that the generative map is continuous. And that'll let us talk about discontinuity of the generative map at a rule, and to develop a bifurcation theory for agent-based models, and even connect ABMs to the structural stability of dynamical systems. So we're going to talk at a very high level, and then we're going to do a specific metric that we can use on trees, that is agent-based models, all right? And again, just to keep everything straight, the generative map is not the temporal evolution operator of the underlying simulation. It's not what happens to X temporally given a fixed rule. That can't be continuous. The map studied here is a higher level correspondence between rule space and the patterns generated. And this is the object that is continuous, I will argue. All right, so with all of that as preliminaries, I want to define the atlas and the whole idea of generative stability first at a high abstract level, and then down in the real world of the flat land of agent-based modeling. So the general setup is this. There's some space of rules, micro-agent rules, and they have a metric, mu r. And there's outcome space of macro patterns, and it has a metric, mu y. In the outcome space are wealth distributions, pandemics, time series, and the metric we've discussed, there's natural metrics for those, and the explanandum, is an open set in y. We say, I want a range of Gini coefficients, or a range of Moran's I, or there's some range of things that qualify as meeting the generative criterion, right? I've generated the thing. The generative map sends the agent rule, again, one rule for expository purposes, to outcomes in U, the target pattern, a level of segregation, wealth distribution, Gini coefficient, what have you. Generative map sends the rule to an outcome. So it maps rules-based outcome space. We're going to say, now a rule is generatively sufficient for the open explanandum if G sends R to U. Now this notation, this means that G sends R to U, G sends the rule into the set I'm trying to explain. That's the same as saying the inverse of G takes you back to R, right? Inverse, that the rule is in the inverse image of G. All right? That's just a way of saying G takes R to U, but it'll be convenient as we go along. And we can now partition rule space into the disjoint union of three sets. The interior in rule space of G inverse, the exterior of G inverse, and the boundary between those. A rule is generatively stable if it's in the interior of the inverse of G. So there's a neighborhood of R, an open set in the rule metric, which G maps to the explanandum, the set we want to grow. And we think of that as open in the Y metric. It's a range, qualitative property, etc. Rules on the boundary of G inverse U are generatively sufficient, so they satisfy the Josh motto. If you didn't grow it, you didn't explain it. You do grow it, but not in a robust, generatively stable way, because there's no open rule neighborhood conserving the qualitative outcome. Now, we'll give a specific metric on rule space so we can actually display the neighborhood, but continue on the assumption of a rule metric at this point. All right? Then we have two metric spaces, rule space and outcome space, endowed with independent metrics, rule metric and outcome metric, and a map between them. The map sends this metric space to the other metric space. And now, what kind of map is G? We've agreed that the output space is open if G inverse, the set of rules that generate U under G, if that is open, then topologically, G itself is continuous due to a beautiful theorem. It says for metric spaces X and Y, a function from X to Y is continuous if and only if, when Y is open, F inverse of Y is open, which is a very different definition of continuity than, I can draw the curve without lifting my pen from the paper, which is the elementary calculus. This is a very beautiful and much more general way of thinking about continuity, and it applies to this situation. The map is continuous if its inverse image conserves openness, and that will allow us to characterize rules in the boundary of G inverse as points of discontinuity in rule space. Rules can be generatively sufficient, satisfying the motto, but they're not generatively stable. generative stability implies generative sufficiency, but not conversely. More interesting still, if that was interesting, the explanans, that is the rule space mapping to U under G, doesn't have to be connected. There can be disconnected, generatively stable patches of rule space, which I've drawn with very high-tech equipment here, that you could have patches of rules, these three lower patches of rules, those are open sets of rules in the submetric, and G sends them all to the same plateau, the same level set, the same explanandum. Okay, so there can be many to one. And we're going to call the collection of those possibly disconnected, generatively stable open rule patches the explanatory atlas of U. So the explanatory atlas is the interior of the set of rules G maps to U, which is to say, it's the interior of G inverse of U. And it's open because it's the union of open sets. So the big picture right now at this point is, if you grew the explanandum U, you have a candidate generative explanation. If nearby rules also grow U, you have a generatively stable candidate explanation. The collection of all such stable explanatory candidates is U's explanatory atlas. And we're going to use either of these notations, A of U, as identical with the interior of the inverse of U, the inverse of U. Or they'll both be illuminating, and I'll go back and forth. So I hope it's not too confusing to have these notations going around. But that's the idea, all right? The idea is it's not enough to just grow it. You want it to be robust to changes in rule space, and we need a metric structure on that to make sense of this idea. Okay? Now, we talked about generatively stable, stable generation. But, rule space, again, decomposes into the interior of generatively stable rules, the exterior of rules that don't get you into the explanandum at all, and the boundary, rules that suffice to get you there, but not robustly. And we've talked about the interior of the atlas, but the other regions are very important. First is the exterior of the atlas. Suppose someone says, R explains U, but it turns out that R is in the exterior of the explanatory atlas. It lies outside the atlas of generatively stable rules, and it's disqualified. But now suppose some smart aleck says, okay, but if I change that rule a little, I get an admissible candidate. That won't fly because the exterior of A is an open set. So there's some neighborhood of R, all of whose members stay in the exterior of the set. So falsification in this sense is also generatively stable. One might want to say that elements of the exterior of A are robustly falsified. They can't be rescued by a small tweak in the rule metric. Just as the rule stands up, a successful rule stands up to perturbation, and a falsifying rule is robustly, it doesn't stand. Okay. Now the third element is really the most interesting, the boundary between the interior and exterior of the explanatory atlas. Now I've used the term boundary because it's the right idea, but because the interior and exterior of the atlas may be the union of disconnected patches, there may not be a boundary in the simple sense that our earlier circle had a boundary. A more general definition, subsuming that one, is the closure of the atlas net of or differenced with its interior. So the closure of the circle diagram is the interior plus the solid boundary. And the interior is just that closure net of the interior. The boundary, is the closure net of the interior. For the circle, it's the dotted interior plus the boundary net of the interior. This is the general definition. Rules on the boundary satisfy this condition. And their points of discontinuity in the generative map. Rules are points, and these are points of discontinuity in the generative map. You might call them bifurcation rules, since any change tips into one of the disjoint sets, the generatively stable rules of the interior and the stably non-generative rules of the exterior. So rules that satisfy the motto, sufficient to generate, but are not generatively stable, are bifurcation rules, points of discontinuity in the generative map. So you can satisfy the motto and not be a robust rule. And that's the kind of very high-level set theory topological picture. But now I want to go down into the ABM case and show you a specific metric that we can work this out. And I'm going to use something called the cylinder metric on trees. And in the 2023 paper on inverse generative, I talk about Hamming distance, Gödel numbering, all sorts of other ways of trying this. And in that article, I sort of threw up my hands and said, darn it, none of these are very good. And in the time since, I've just kept studying. And this is a metric that I think has some chance of working. Excuse me. So a movement rule, again, let's go back to the rule we showed. I'm not going to read through this again. It's just a tree, a decision tree. The cylinder metric between two trees, and again, I'm identifying agents as rules and rules as trees. These are agents. The distance between them in the cylinder metric is 2 to the minus k, where k is the depth of their shared prefix. If you start at the top and go all the way down to the point where the trees diverge, the depth to which they agree is their distance. And 2 to the minus k is the depth of their shared prefix. And 2 to the minus k is their distance from one another. So here's the one we just saw. Here's two rules. If you're unhappy, if you're not unhappy, stay. If you are, look for a vacancy. If there is one, move. Otherwise, stay. And extend it now. The same for opening trees, branches. And then if there's a vacancy, no, stay. But instead of yes, move, it's yes, well, how expensive is it? If it's free, move, it's expensive, don't. So the right rule is longer than the first, but they agree to the depth 4. So their distance in the cylinder metric is 2 to the minus 4, or 1 over 16. The metric is bounded by 0 and 1, because if there's no agreement, it's 2 to the minus 0, so distance is 1. And so forth, as n gets bigger and bigger. The deeper the agreement, the closer they are in the cylinder metric. And if they're in huge length and agree all the way, then their distance is 0, all right? And this, once you see 2 to the something, you immediately think of an information theoretic move, and you could imagine that if k equals 1, then minus log d is 1, and so a single agreement is worth 1 bit of information. Okay, now, interesting question here is, suppose two rules share almost the entire tree, however deep it is, but they differ in the final leaf. One ends in move, one ends in stay. Now, trees can be arbitrarily close by letting their depth go to infinity and just have their last leaves disagree, right? So the outcomes can be diametrically different, even though they're arbitrarily close in this syntactic formal sense. That's good, because now we have one of the things we wanted. They can be close in rules and diametrically opposite in outputs, which we couldn't get from the naive interdefined move of the rule is small if and only if the output is small, and so forth. So this gives us, okay, now we can say that coherently. We can say the rules can be arbitrarily close, but the outcomes diametrically different. And you might think of it, speaking loosely, that they're close syntactically, but remote semantically. What they mean for output is different, even though they're close in their structure. So that's good. That's one thing we wanted. And we can also get the reverse. We can have the case of rules that are maximally far apart, but generate nearby outcomes, suggesting that they live on disjoint patches of the explanatory atlas. And a nice example comes from this work on inverse generative social science. We guest edited a section of the journal. Bill Rand was one of the guest editors, if he's here. And this is an example from that. Just a quick aside on inverse generative social science. I mean, the agent-based model, in my view, is the principal scientific instrument of generative social science. Typically, we design completed agents, fully endowed with rules and parameters, to grow macroscopic targets from the bottom up. Inverse generative science stands that on its head. We don't handcraft completed agents to grow a target, which is sort of a forward problem. We start with the macro target and evolve micro agents that generate it, stipulating only agent rule constituents and permissible combinators. No fully assembled agents. It's just constituents. And the fitness of the agent is it generates something, and if it's proximate to the target, then it's fit. And it gets to have sex and offspring and mutate and do all the fun things trees do. So the idea is, rather than specific agents as designed inputs, we're interested in agents as evolved outputs. And in the article that needn't detain us, there are all these requirements for that. You got to have a target. You got to tell me what the constituents are. How can they combine? How do you define fitness? What algorithm are you using? Is there a stopping rule? And in that collection, by this method, all sorts of interesting things are evolved. Reference behaviors are, this pattern on the left, and the learned behavior is on the right. Obviously, you'd want some quantitative metric, but for drinking behavior over the long term, polarization, common pool resource experiments, these are all examples in the collection of the inverse generative method producing rules that are successful from just primitive, Darwin's warm little pond of constituents. Okay? Now, the next one makes our point very nicely. This is work by Chatika Gunaratne, Erez Hatnami, and Ivan Garibay on mixed segregation patterns that are a departure from Schelling's famous segregation model. And the idea was, no, let's not grow segregation, let's grow something that's more mixed. And to do that, we used an extension of the behavioral repertoire that Schelling used. Schelling's model, Schelling's agents, care only about the racial composition of your current neighborhood and the candidate neighborhood. We added the neighborhood age. You might want to live with people of your own age. The distance from your current location. Maybe you're just a loner who doesn't really want to be around anybody. You might have a history of movement, and you might ask how happy the people in the neighborhood really are. And you can add these, divide them, multiply them, allowing very highly nonlinear rules. And the top 10 evolved rules are these. And I love that the winner, at least as far as we studied, is just Schelling's. It has Schelling's rule in the denominator. It says your propensity to move divided by Schelling's sole consideration. So I think it's cute to say inverse generative social science produced the inverse of Schelling's rule. But that's not really the point. Another point is that it's obvious there's no monotone relationship between rule fitness and rule complexity. You have excellent rules that are simple and crappy rules that are simple and lots of rules in between that are complex. So there's no monotone relationship between fitness and rule complexity. So here are the top 2 rules rendered as trees. These are the rules. These are them rendered as trees. And you can see that they actually don't even have their first node in common. This one says divide. This one says multiply. So it's also sort of fun that Schelling's rule is conserved over computational evolution. Here it starts, it remains, but it's an element of a more highly evolved tree. All right, so point was, here are the rules. These are the two top rules. We were interested in this other case of a large rule change with a small output change. And this illustrates that. Since they share no nodes, these rules are a maximum distance apart. But they generate outputs only 0.04 apart in the HATNA C index. So if we think of moving from the first place to the second place rule, we have a good example of a maximal change in rules producing a small change in output. These two rules might reside in disconnected rule patches mapping to the same explanandum plateau. And that can happen. Disconnected patches could be rational actors on one patch and zero intelligence traders on another, and their trees could look utterly, they don't overlap at all. Okay, so now we've achieved one of the things we wanted. We have the possibility of arbitrarily small rule change in the cylinder metric with maximum change in the output metric. And we can have maximum rule change with small change in output, and exactly the two cases that are precluded when we interdefine them. So we can have big rule change, small output, big rule change, big output, small, 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 big. Okay, good. So we have the cases that we're missing in the interdefined mistake. Now, prefix determinacy means that membership in the explanandum, that is to say, rules that generate the explanandum, are determined by a finite rule prefix. If they agree down to that depth, it doesn't matter what happens below that. That would be prefix determinacy. And then for every such rule, yes, there is an open cylinder neighborhood entirely contained in G inverse of U, entirely contained in the atlas. That's a proof that will be published. But by the earlier theorem, G is continuous again. And since all these rules are in the interior, they're generatively stable because it's open. That's a little tough to follow. Suppose membership in the explanandum is determined by a finite prefix, meaning that everything below the shared prefix is irrelevant. Then for every one of those rules, there is an open neighborhood entirely contained in G inverse of U. So it's in the atlas because it's in the interior of this inverse. And by the earlier theorem, G is continuous. And since all of these rules are in the interior, in the atlas, they're generatively stable. Now, most agent models and many other models involve randomness. And we need a notion of stochastic generative stability, and we need to think about the stochastic generalization of the explanatory atlas, the stochastic atlas. And, again, we typically involve randomness, first the general move, then a toy example. The generative, the abstract move is R is rule space, Y is outcome space, delta Y is the set of outcome distributions, and the stochastic map takes a rule in the rule space to a distribution of outcomes in the outcome space. For each rule R, G produces a probability distribution over outcomes, as when we do different random seeds. We have the same rule, different random seeds, you get a distribution of outcomes. The deterministic case we talked about, and it's the degenerate distribution. And the stochastic atlas, or of stochastic generative stability, the stochastic atlas becomes this. It's the atlas, G inverse of U, with some probability threshold. I'm saying, now I'm looking at the rules in R whose probability of generating U is greater than some threshold, P star. Okay? So it's a very simple move. I'm saying, it's in R is explanatory if the probability of G of R being in U is greater than some threshold. All right, and it's stochastically generatively stable. Stochastic generative stability of the rule becomes the interior of this new thing with a distribution. Okay? So now back down to a concrete example in the cylinder metric. Now we're back in an actual world. Let U be the phenomenon we're trying to generate with, the segregation index. And to ensure openness, let's just say success is the index greater than 0.7. P star is the probability level we regard as success. It's the relative frequency with which our stochastic realizations generate outcomes in U. So here are 3 agent rules. Same tree, except one ends with move to a random vacancy, the other ends with move to the nearest vacancy, and the other ends with move to random vacancy within radius 5. I'm going to run them, 15 times each on a 25 by 25 torus, constant population, fixed agent density, and you're unhappy if the like myself neighbors are less than 40%. All right, so what do we get? We get that rule 1 has a mean over these runs of 0.824, so it's inside the acceptance region. Rule 2, move to the nearest vacancy, is 0.709, so it's also inside the acceptance criterion. And R3, move to a random vacancy within 5 spaces, is 0.786, so also inside. So for that explanandum, C greater than 0.7, all 3 are in the interior of the generatively stable set, interior of the atlas. And an interpretation would be that, heterogeneous agents, each equipped with one of those rules, will also generate outcomes in U. We can put all of that in a matrix. The distance metric from R1 to R1 is always, the diagonal is 0 because my distance from myself is 0. And otherwise we can fill out all the other distances and get a square symmetric matrix. And we can do spectral analysis on that and try to use this to get the cartography of the atlas. So there's a similarity matrix whose entries are 2 to the distance between rule I and j. Nearby rules have large similarity, remote rules have small similarity. And, we can take the eigenvectors of this matrix to detect patches in the atlas. So for the toy segregation examples, those rules had high similarity, and the leading eigenvector assigned them nearly equal weight. And this identifies a single explanatory patch in the generative atlas. But suppose we have rules 1, 2, 3, and rules 4, 5, 6. These are different provinces of the explanatory region. And suppose we posit that the within province similarity is high, but the between province similarity is low. Then the similarity matrix becomes this, and the second eigenvector is 1, 1, 1, minus 1, minus 1, minus 1. The change in sign identifies a major explanatory split. So separate explanatory provinces of the atlas are indicated here. Okay, so high eigenvectors identify subprovinces within continents of the generative explanatory atlas. So the spectral analysis of the similarity matrix allows us to map out this atlas in some way. And I think one agenda for inverse generative social science is to explore, we generate these nice rules. Now use computation to study their neighborhoods, vary them a little under now a term we can make sense of, and see if they're generatively stable, they're robust. It's not just, I dreamed up this rule and I grew this thing. And, people can say, well, that's just ad hoc, and is it stand up to any variation? Now we can answer that, at least pose the question clearly, if not answer it perfectly. And generative sufficiency, a la the motto, is just a point property. And generative stability is a neighborhood property, quite like structural stability of dynamical systems, which I want to talk about now. And the whole topic of agentization, where you start with a dynamical system and you agentize it and assess the generative stability of the agentization. So a very beautiful idea, again, in mathematics, is the idea of structural stability. And this involves dynamical systems like the predator-prey model, the SIR model, the Richardson arms race model. But in generally, you have the growth rate, that's a typo, dx dt is some function of x and y, like predators and prey, and dy dt is a different function of x and y. It should be dy dt. And these have what are called phase portraits in the xy plane. So predator-prey produces spirals, ellipses, I'm sorry. But there might be spirals and other shapes with equilibria. And we're not going to focus in dynamical systems and structural stability. We don't focus on x and y as functions of time, but we focus on the motion in the xy plane itself, which is called the phase plane. So in the phase plane, I don't care what the solutions of the predator-prey model giving me prey at time t and so forth. I care about prey against predator, and is there cycling? Against time, you'd see waves like this. But in the phase plane, you just see closed orbits, okay? Now, a homeomorphism is a transformation that deforms phase portraits, but preserves the number and stability of their equilibria. It's the qualitative flow we care about. We might get deformed ellipses, but we still get ellipses. And as we change the algebraic form of the system, again, not parameters or initial conditions, but the algebraic form of this FG pair, this vector field, do we get the same qualitative behavior? And the whole approach is due to Henri Poincaré, who called it the qualitative theory of differential equations, because we don't care about the solutions in time. It's kind of the way I teach it is everything you wanted to know about differential equations without solving them. And it's revealing in ways the solutions are not. But again, back to the theme, structural stability relates a metric property, a distance between vector fields, to a topological property of phase portraits. They're deformable onto one another. And if I can change the algebraic structure of the vector field in a way that preserves the qualitative phase portrait, then I say the field is structurally stable. And that sounds a little bit like what we're worrying about. Right? We're relating a metric property, the cylinder metric, to a qualitative property in output space, openness of U, the explanandum. And again, homeomorphism is basically like caricature, right? Two orbits of a vector field are homeomorphic if there's a continuous structure-preserving function mapping each to the other. So they're like caricatures, really. Smooth deformations, like characters of Lincoln. And I discovered when I was looking for caricatures of Lincoln, there's this great book in 1903. There's a whole book of 32 great caricatures of Lincoln. So it's a book of homeomorphisms. And they're wildly different, right? But they share Lincolnness. And for a dynamical system, Lincolnness is the number of equilibria, their local stability, and the flow's direction in time. Okay? Now, agentization. What I'd like to show is that I can define agentization in a way that structurally stable dynamical systems have generatively stable agentizations. And that would connect these two fields in a very interesting and novel way, I think. But again, a field is structurally stable if there's a neighborhood, all of whose members have homeomorphic phase portraits. Each can be continuously deformed into the other. You can't rip it or have any self-intersections, but all the weird deformed ellipses you like and so forth, all right? And again, it's very beautiful in relating a metric property, the neighborhood of a dynamical system, to a topological one, homeomorphism on phase portraits, unlike many beautiful theorems and other things. It's beautiful in this hidden equivalence of seemingly unrelated properties. A metric neighborhood conserves a qualitative property. And generative stability does this too. It conserves a topological property, openness of the explanandum, U, with a metric neighborhood of generative rules. And if we could relate those, it would unify differential equations and agent-based modelings in a way that's totally different than mean field theory. The mean field, we need, I'll come back to that, why it's different than the mean field. But what do we mean by agentization in the first place? I've got some dynamical system, which typically in an epidemic model, it's continuous pools, susceptibles, infectives, predators, prey. They're just mixing pools. there are no individual agents. So agentization, step one, go from continuous pools to individual agents. They're homogeneous. They don't differ from one another. Make them heterogeneous. They don't mix perfectly. There's some notion of localness, local interaction. It could be network, local, or spatially local, but there's some way to talk about direct local interactions between the agents. And the dynamical system is deterministic, and the agentization is stochastic. So deterministic, you might have a fixed probability of transmission per contact. Here, the actual transmission that occurs is the draw from some distribution. All right? So you make it individual, heterogeneous, local, spatial, and stochastic. That's an agentization of the dynamical system. And the conjecture is this. Mean field theory asks, do stochastic realizations converge in mean to the ODE's solution? That's what the mean field theory is interested in, is here's the actual solution. And instead I've got this distribution around it. And do the realizations converge on average to the ODE single solution? But we're asking a totally different question. We're saying, can I stipulate an effective, that is algorithmic agentization procedure under which the agentization of a structurally stable dynamical system is generatively stable? And that is, structurally stable dynamical systems have generatively stable agentizations. That's a conjecture that I think I can prove. But that would bridge these fields in a radically different way. So far we've just talked about topology. The atlas is a set of generatively stable candidates. Is there anything missing from that? The atlas is all generatively stable rules. But, do they make sense for humans? There's this other consideration, which they could be high probability in the sense that the relative frequency of the outcome is high, but they might not make sense, right? So one motto refinement that I published after the original motto is to explain a social pattern, one must show how the pattern could emerge on timescales of interest to humans in a population of cognitively plausible agents. And I developed agent 0, completely in NetLogo, by the way, as a cognitively plausible formal alternative to the rational actor. And its plausibility is based on some cognitive neuroscience, and I leave it for you to judge its success. Recent work underway with my great colleague Francesco Renzini, called Fear and Financial Contagion, Modeling Animal Spirits in Asset Markets. This uses Agent 0, a variation on Agent 0, to study financial contagion and market dynamics. And Francesco and I are toying with the idea of calling this line of research fearonomics, since fear plays a huge role in all of it. But we're not convinced that's the world is ready for that yet. And it's a preprint that's available for people to read. We love comments, so please feel free. So, should we give one region of the atlas more credence than another? The atlas is just topological. It says this maps into the thing, but it might map in crazy ways. It might say, there might be rules that are interior to the atlas that are still cognitively not plausible. You might say, if the agents have infinite memory, or boundless computing, or other kind of obviously implausible attributes, then, we're not going to include them as serious candidates. We want stable generation by plausible rules, and I think the set of those is really the explanans. It's the set that explains the target phenomenon. Now, everybody makes this judgment implicitly when we choose any rule. I mean, economists' maximum utility, they regard that as cognitively plausible. Solve for the Nash equilibria of a game. Zero intelligence trader. LLM trained economic agents. I mean, whatever we use, we're making some judgment. You're doing it in any field, like it or not. So, let's do it explicitly and give a concrete example for trees. But in abstracto, again, let's imagine a plausibility function over the atlas. Then we could posit that the generative explanatory object is really an atlas equipped with a plausibility measure. And P, of course, acts on elements of the atlas. So we can write that as the atlas of U and the plausibility of it. things in the atlas, and if they're, if they're ruled out, they're ruled out. So we're going to confine ourselves to the interior and the plausible members of that. And robust explanations are in the interior. Now, physics and social science, I think, share this topological structure, but have different probability standards and different plausibility measures. I think in physics they're identical. But physics is sort of monist. It's a monist science that has one plausibility. It's the delta function with all plausibility concentrated on laws, like the law of universal gravitation. And we don't ask, what happens if I change the law of gravitation a little? It's just because we know this is the solution. And I think physics envy is sort of the longing for monistic laws. But social science, I think, should be pluralistic. P, the plausibility function, could be a measure, has its mass distributed over generatively open rule patches. And P ranks the possibly disconnected, generatively stable explanatory candidates. So the atlas is topological and probabilistic. P is cognitive. And a plausibility measure on the atlas, again, is the union of the generatively stable regions. P can have all kinds of shapes, this plausibility thing. It could be flat, like a uniform distribution, or bell curved or skewed. And the plausible P and sufficiently probable P really form a kind of truth table for the atlas. If it's plausible and meets the probability criterion, then yeah, it's explanatory. And I thank Francesco for a nice discussion of this, a clarifying discussion of this, that you have all these possibilities. It could be plausible but improbable, not plausible but highly probable, not plausible and not probable. And all we care about is the first line. The full atlas, then, is really the union of the overlapping regions that are sufficiently plausible and sufficiently probable. So the real object is the union of these intersections between plausible and high probability regions. And I think we need that to really execute Charles Sanders Peirce's abductive idea of inference to the best explanation. It's implicitly pluralistic epistemologically. I think social science has to be. We're talking about explanatory regions, not, GMM over R squared. All right? So if a unique best one of those exists, it would be the rule that maximizes plausibility subject to being in the atlas, right? It's the most plausible rules that are generatively stable. The most plausible of the generatively stable rules. If that exists, maybe that's the best explanation. And it would be not just necessary, as in the motto, but sufficient, which is an advance over just the motto. All right, so summarizing, we have a stochastic explanatory atlas, which is the interior of the generatively stable rule set that meet the probability standard. It's generatively stable if the rule is in that pair. It involves probability over realizations, but we also require cognitive plausibility. And, again, cognitive plausibility, well, that's wide open. But, minimally, you could just say P is an upper bound on tree depth. And in the inverse generative work, we actually penalize rules for their depth. But mathematically, you could say it's plausible if it's, if it takes the map to 0 and 1. The best stochastically generative stable explanation is, again, formally the same. It's the rule that maximizes the plausibility of R, of all the R's in the generative stochastic atlas. So from the complete set of generatively stable candidates, this is the group we want. Okay, couple closing thoughts. The generative atlas of social science is a vast, patchy, largely unexplored place. And I think of Newton's great remark that after studying gravity, I do not know what I may appear to the world, but to myself, I seem to have been only like a boy playing on the seashore and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me. So I think what we're doing as a community is exploring this area. We use intelligent design, handcrafting, but we also use evolution, IGSS, machine learning, large language models. These are all ways of probing the explanatory atlas. They're all hands on the generatively exploratory elephant. And I think that is the collective enterprise that our community is engaged in, actually. Again, classical mechanics is really a special case of generative social science. For mechanics, the probability criterion is that it has to be 1. And the plausibility is focused entirely on the law, the Dirac delta function on the universal gravitation law. There's no distribution of plausible gravitation laws. And for generative social science, there is. We don't require that the probability be 1. We're content to have it be, if I get the right thing, 90% of the time, I'm good. And again, there are lots of things that could be plausible. And the epistemology is by nature a pluralistic enterprise, right? We're interested in many different things that qualify as explanation, and maybe heterogeneous agents are equipped with different things from that set. And in the old philosophical tradition of logical positivism, you might call this topological positivism, but I don't want to get into that, all right? A second case, a thing to think about is, how do we think about scientific progress? You could think of scientific progress as atlas change or atlas evolution, new instruments to go back to this collection of things in initial conditions, parameters, the telescope, the microscope, those things can help us measure those better and can wipe out entire patches of candidates or discover entirely new ones. And new theories can displace existing ones. Sometimes the processes of theoretical and empirical development are asynchronous, as in the many cases where new theories precede data. I mean, I think social scientists are taught, always grub around and get a ton of data and then try to figure out a model. But in physics and in a lot of the sciences, including the social science, the theory precedes the data and tells you what data to go collect. So I like that approach because I don't like data. But now, of course, the scientific community may be slow to change their plausibility metric, even as the probability approach is 1. But this is a separate sociological Kuhnian issue, distinct from topological structure. And if I were forced to use Kuhnian terminology, I might say normal science is the smooth deformation of the atlas, where scientific revolutions are cases in which the two atlases are not homeomorphic. Entire patches are created or destroyed. And might be a better, more topological framing than Kuhn's really unsalvageable idea of incommensurability that we can come back to. But this is an idea of scientific progress. And if I may, this is just a personal reflection. Uri was allowed some personal reflections. So I'll give this one. What is a small change in rules? Really innocent looking question. But it stayed in my head for a long time, for about 30 years. And at the same time in my head were several beautiful ideas in mathematics. That conservation of openness, inverse conservation of openness is continuity. What a wild thought. Structural stability of dynamical systems. And all this junk bubbled around consciously and unconsciously in my head for many, many years. And if you read, Hadamard wrote a great book, The Psychology of Invention in the Mathematical Field. He talks about how much of the work is unconscious. And there were days when I woke up to some consolidation or some distinction that I hadn't realized was important. And so my advice to the budding theoretical person is, in your head, carry around only the most beautiful things and the most vexing things. Everything else is clutter. Let them bubble around. And if you're very, very lucky, the beautiful things will resolve the vexations. And if you're super lucky, they do it in a beautiful way. I'm not sure I've achieved that, but that's the aspiration in general. Okay, so I thank you. I thank Uri. Most recently, I thank the Yadon Foundation for funding the sustainability of this great community and NetLogo, the centerpiece of it. So thank you very much. We're colleagues. You can email me with objections, thoughts, what have you. I know that was like trying to get a sip of water out of an open fire hydrant, but maybe you have questions or please feel free to ask or comment or what have you. Please, go.
Okay, great. That was really cool. I mean, that was really cool. That was such a great talk. But there's one thing that's just sticking in my head.
What the hell are you talking?
Me.
I had a student who had the same thing. I said, your talk was amazing. I only have one question. What the hell are you talking about?
No, okay. My question is, I'm not convinced the inverse exists, because the inverse only exists if G is a one-to-one mapping. But for any tree that you give me, I can rewrite the tree to change the order of the nodes.
But then
if it's vacant, if it's vacant, don't move. If it is vacant, are you happy? That's maximally cylinder distant, but it maps onto the identical point of view. So there's no inverse because I have two different trees that are maximally different that map onto the same point of view. And that's kind of sticking in my head. If there isn't an inverse, how do you deal with this?
Well, again, what is the thing that I'm claiming has an inverse?
You're claiming that there's an inverse of the mapping from the rule space to the space U.
Right.
And so if there are two rules in the rule space, two separate points in the rule space that map onto exactly the same U, then how do you map from that point in U? Which rule do you map back onto with the inverse?
Okay, fair question. Would you be content if I called it the pre-image of U rather than the inverse?
Okay, so explain a little more, because
I'm interested in
sure I know
all the rules that generate U.
Yes.
And G inverse of U is a rule. It's
Yes.
the rules that generate U under G.
Mm-hmm.
And the collection of those I'm calling the inverse of U, but it's the pre-image of U under the mapping G. It's everything that G maps to U. It's not like an inverse of a function like x squared.
Mm-hmm. Okay, so I can have multiple points
Right.
in R that map onto U, and
Yep.
as long as G inverse maps onto some point back in R, it doesn't need to be the point that as long as it maps onto some point in R that will then map back onto that.
You're good.
That's cool, but now you don't necessarily have a unique measure of the distance between two rules that produce the point in U.
You're saying if I flip the, but I think I have a unique distance for any two rules.
Right, but if the two rules, but that's the thing, is if the two rules map onto the same point in U, then they're maximally distant, but they map onto the same point in U.
Brilliant.
So which one do you use as the reference for measuring distance when you change a rule?
Okay, good questions. All I'm claiming is that you can have that case where the rules are arbitrarily remote and map onto the same outcome, which would indicate that you might have very different types of explanations. You might explain segregation by racial preference, but you might explain it by, income differences. Or Blake and I were talking about the Anasazi model. They'll get into the terminal positions running, moving backwards and completely drunk. But that's not an admissible rule. But I take your point.
I'll think about it, but thank you for giving me a lot to think about.
Thank you, and likewise. Thanks. Sir.
We're going to do a lot here. I was just wondering, this is slightly less theoretical, but how would you generate, using the IGSS sort of framework or that kind of a model, or you're evolving these rules or these rule sets, stochastic rules? Because I noticed there was an example for the first one, but not for the stochastic rule sets, and that seems like it would be like a difficult case.
It's a different case for sure, but again, I mean, it's formally, you're still mapping. G is stochastic, and it takes rules to some region of output space, right? And rules are proximate stochastically if those regions overlap with high probability. So the idea was inverse generative social science gives you generative rules, but we want to look farther and perturb them and see if they're stable. And I think the same would apply to the stochastic variant. It's just that stability would mean, membership in, in some, that the probabilities are in the same neighborhood. Maybe. They're good questions to think about.
So, Josh, thanks again. That was fantastic, as always. And I think your quote about sipping from a fire hose is perfect, because I do think there's a lot in there that I'll be thinking about for a while. Hey, one thing that kind of, in similar space to some of these questions, the question of the distance metric was kind of floating in my head a little bit. Specifically because you showed that example from Chatika's work, right? Where at the top node, there's a multiply and a divide, right?
Right.
The question I'm wondering about is like, do we need to do anything to account for the type of operators we're using in these trees, right? So if I don't allow divide as an operator, right, then it might very well be that I wind up with the exact same rule again because I'm just multiplying by a small number, right, which would be the same as dividing by a large number, right? And so then, I guess the question, like I like the idea of having syntactically different rules that result in the same, like almost, I think that is almost genotype to phenotype mappings, right? Like that result in the same phenotype even though the genotypes are different. But if I constrain the alphabet by which I construct that genotype, I may not result in those same large differences. And does that matter at all, right?
Well,
I guess is the question I'm trying to figure out. I don't know if it impacts anything you're saying. I'm just trying to figure out whether it does or not. Yeah.
That's a good question. I mean, I think in the case you gave, their metric distance would be positive, right? I mean, it might also be the case of the sort we're talking about, where the rule difference is huge, but the output difference is small. And that's not troublesome, that's a good thing. That's a feature, not a bug, you know?
Yeah, I guess what I would think about is if all of a sudden just changing the alphabet changes the distance, right? Does that then affect what these patchy regions look like, right? And so does that become like a traditional science where it's just a small deformation versus the Kuhnian approach where, if I throw in whole new operators, I can move to a completely different space? I guess that's what I'm trying to wrap my head around. It's like, how does changing the input to the rule sets affect the space of plausible and probable rules that I could come out with?
Right. I'm not sure. Can I calculate the distance between the two rules you have in mind? If so, the whole thing goes through. And if not, then it's a separate and interesting question. Sir?
I think a big confusion might be the difference between distance and agreement. Agreement to k depth is not equivalent to distance between rules in a rule space. So I think, if, like they were saying, or him, I think, how you structure the trees, or whether they agree at all, how are you quantifying distance between rules? If you agree to depth k, and then
the distance
on the
is 2 to the
left side of
minus
the tree, it's just agreement, right?
It's the depth of agreement, and that if that is k, then the distance is 2 to the minus k.
Okay.
Yeah.
But if the trees go on forever in completely different semantic and syntactic rule spaces, we're just going to call that 1/8 if it's,
Yeah. But you can differ in the terminal leaf and be arbitrarily close in the cylinder metric. The trees could agree out to the 1,000th depth, but the terminal leaf says kill your mother and the other one says save your mother. Maybe that's not answering your question. I'm not sure.
I just think that's the common confusion of agreement depth versus.
Yeah. I should also say
rules.
the distance.
Exactly, and you can preface a tree by a whole bunch of if true on the top, so you can make the distances arbitrarily small. For the same effective change in the algorithm, you can make the distance arbitrarily small by putting a whole bunch of if true leaves at the top of the tree. And the distance can always be made arbitrarily small for any change that you make.
Right, or all sorts of relevant extensions on either side. That's a nice point. The metric, I think, assumes they start at the same. You start at one level of the node. But you're quite right that in general you could add all sorts of prefixes beyond those. But am I answering your question? The distance is simply that's okay. The depth of the agreement is k. 2 to the minus k is the distance between the trees. But I'm not wedded to the cylinder metric at all. There might be all kinds of other metrics that instantiate the topological picture better or more fruitfully. It could be the number of common leaves or the maximum, yeah.
Okay, we're gonna take one more question. We're good over time.
Good.
And then anybody wants to stick around, if Josh, if you want to stick around.
Sure, I'm
we can
cool.
Have some more discussion.
Thank you, Josh, for
Yep.
the talk. Elaborating on the first question, I was wondering actually how important is the mapping between the root space and the outcome spaces bijective?
I don't think it's important.
Not important.
No.
Or up to a metric. I mean, it's not important to find a metric that perceives bijection between the two.
Bijection between
The
the
root space and
the output space. I'm not sure the mappings have to be exhaustive of U. Right? I don't need that everything in U. Yeah, everything in U requires a rule that generates it. So maybe it does have to be bijective in that sense. I don't know. Help me figure that out. What do you think?
I don't know either. We have to think about
Yeah.
Well, you could have many to one and one to many.
Well, that's what it is, many to one.
Yeah. You could have one to many. One rule generates many outputs.
Okay.
I guess so, yeah.
That was going to be the last question, but Uri wants to ask a question, which doesn't count. So.
Okay.
This will be our last question. That people can have.
I just have a question or a comment. First of all, brilliant.
Thank
Of course, as you always are, and very thought-provoking. I'm not trying to follow all the details, but
I'm not sure I do either, so that's okay.
but I mean, it's been extremely frustrating to me teaching a small number of years that when people try to do sensitivity analysis, and the sensitivity analysis is based on a set of parameters that seem very meaningless to whether the explanation is a good explanation or a wrong
Right.
explanation. And now you're providing could do that now. So look more deeply at it to see if I can make it work.
That would be a triumph if we could. Let's do that. Let's figure out how to make NetLogo search for these generatively stable rules, search the neighborhood of rules in a rule space. That'd be fantastic. I'd love to do that.
Okay, let's give another round of applause.
Thank you.
Thank you, everybody. We have one more day tomorrow, so I hope we'll see you all again tomorrow for some more presentations and workshops. Have a great evening.
Josh, Epstein.
Okay, that was really fabulous. I will follow up by email if you don't.
No, they're very,
because I
very
think
sensitive
there could be some good questions. And, I mean, one thing I'm thinking about, kind of getting back to your pre-image question, is one approach I'm thinking is thinking about this like squares and square roots, where 1 and minus 1 map, and then you take the square root and it goes back to 1.
Right.
And so you could think about just, okay, let's just run this through. In calculating distance, let's run this through map from R onto U and then map back to R and take